Vale, pues empezamos. Es para mí un placer presentar a Andreas Defant de la Universidad de Oldenburg, que bueno, es casi como de la casa, o sin casi es de la casa. Si me cuento mal, hay al menos 1, 2, 3, 4, 5 de las personas aquí presentes tienen algún artículo con él o más. Yo que sé, lleva visitando Valencia desde hace más de 30, 40 años, otro más, 6, ya son 6 autores. Y bueno, va a hablarnos hoy sobre constantes de proyección para espacios de polinomios múltiples.
Thank you very much. Okay. Thank you very much for inviting me again. I mean, I always feel very well. I see many friends, I see many co-authors, so this will be at some point coming. Oh,
could you
okay.
right there? Is for
Yeah, okay. Okay, so it's great after these 3 years of pandemic and to give a talk here. So I talk about projection constants of spaces of multivariate polynomials. Manolo already complained that he doesn't understand multivariate, but I will try to explain this. I mean, it just means many variables. Okay, so we are so at the beginning of the pandemic. I mean, here are 3 Argentinians: Dani Galitera, Pincho, and Santiago Muro, and this is Mietek from Mietek Massivo. I mean, many of you know him, so these are the names. So they asked me whether we can start some joint work together, and we started with Zoom. And I mean, now we collected many different things, and I would like to explain some of these things. Okay, so this is the team, and some of the theorems will have a team, and then all this means that I produce them with these people. So let me start with. I have a sort of starter here. It's on projection constants, and the projection constant, I mean, can be motivated with the Banach theorem. So I mean, you have a Banach space, you have a subspace, and then the Banach theorem says that if you want to extend to the real, or if you want to extend some operator which has values in R or in C, I mean, then this is possible with the same norm. So the norm is the norm of T. So this is the Banach theorem. And the first question that one could, in order to motivate what is coming, I mean, you replace these scalars by any Banach space. So you fix a couple here, replace this by any Banach space, and try to find an extension less than a constant C, fixing the constant. So how are the couples looking such that for every operator with values in Z, you find an extension with this property? And it's very simple, of course. I mean, a sort of simple exercise to show that this is only possible if and only if, I mean, you find a projection here. So this is possible if and only if X is a complemented subspace of Y. I mean, the proof would be, I mean, you just put here the identity, and then you can extend the identity, and this extension, so this identity tilde would be the projection, and vice versa. It's also, of course, very similar. So this leads to the following definition, which I maybe fix here. I mean, so if you have a couple, so X is a subspace of a Banach space X, then the relative projection constant is just the infimum over all projections. So P is a projection onto X, all projections onto X. So this is the definition. So this is the best constant which you have here, or equivalently the best constant you have here. So it's a sort of graduation, if you want, of the Banach theorem, and this is a very important notion in Banach space theory. I mean, studied by many people, and it's also important in approximation theory. So, for example, if you look at this is also a sort of exercise. If you have a projection P, why is it important in approximation theory? If you have a projection P onto X, then in approximation theory you want to know, given some Y, what is the distance between y and the projection of y under P, and then, as I say, a simple exercise shows, I mean, that this up to this constant 1 plus this relative projection constant times the distance, so this inequality here, I mean 2 minutes and everybody could prove this. Shows an important notion in approximation theory. Second definition, I mean, this is the relative projection constant. So the projection constant of x relative to y, relative projection constant. And there is the absolute projection constant. I mean, here basically you just look at the soup of all relative projection constant x, some isometric subspace of y. Yeah, I mean, here it's written a little bit more sophisticated. I mean, you take x, a Banach space x, and then you take all isometric embeddings of x into y and look at the relative projection constant of I, x, and y. This is the absolute projection constant. Okay. So I think I keep this here. Then, so a very simple, again, a simple consequence of the Banach theorem is that these two numbers are equal and 1. I mean, basically, I mean, you just have to know that a consequence of the Banach theorem, or an equivalent formulation of the Banach theorem, that there are norm-attaining functionals. I mean, then you immediately see that the scalars are always one-complemented in any Banach space, and this is this point here. Okay, so for my purpose, the following is crucial. I mean, I will usually look at x finite dimensional in this talk. I mean, if I go back, you know, many. I mean, of course, not every subspace is complemented in a superspace Y. For example, the zero is not complemented in L infinity, and I mean, this is well understood in Banach space theory. So in most of the cases, these relative projection constants are infinite. Yeah. So, but in my case, I will look at x finite dimension. Then this is a number here. Yeah. And so one can show that if you take a finite dimensional subspace now S, not X, of C of K some compact space, then the absolute projection constant equals this relative projection constant. Yeah, so if one wants to understand this projection constant, absolute projection constant, since any Banach space always sits in the space of continuous functions, I mean, at least in the finite dimensional case, you can concentrate on this relative projection constant to understand this relative projection constant. Yeah. It's also not complicated. And one of the first things one has to learn here. So in the following, I will try to concentrate on this. Okay, so in order to get some orientation, there's a famous theorem, the theorem of Kaditz and Snobar, which says that if you take an n-dimensional Banach space, then the projection constant is always less than the root of the dimension. So then we already know that for an n-dimensional space, the projection constant is always between 1 and root of n. So there are now, this was a very deep theorem at the beginning of the 70s. There are now nice proofs using the theory of absolutely summing operators. And I mean, this is not the end of the story here. I mean, concerning this theorem, I mean, a lot of work has been done on this theorem. For example, it's known that this is not, I mean, you can subtract here a zero sequence which exponentially fast goes to 0. So the projection constant of an n-dimensional space is always really less than root of n. But so I mean, there are many theorems who say this theorem in a certain sense is optimal, and in another sense it can be improved. Okay, but the point is, this gives you orientation. How big is this number? Okay. So, and then of course the next step was to understand the projection constant of LNPs. So Cn or Rn with the p norm. And I mean, so if you want to understand this first theorem, I mean, if you have a Banach space Y and some Ln infinity sitting isometrically in Ln Y, then it's always projected, because if you look at the identity, the identity with values in Ln infinity can always be extended. I mean, the Banach theorem for vector valued is not true, but for some spaces it is true. Basically for spaces which look like L infinity. So if you take the identity here, then you can component-wise extend and get an extension, get a projection. So this is again true. But then it gets complicated. I mean, so here, for example, I will show you a lot of formulas of this type. These formulas are not, maybe you should even not look at them. There are 2 points. If you go to the Hilbert space, first point, I mean, in the complex case and in the real case, the constants are different. Then second, I mean, there is a nice integral formula. So I mean, here you integrate this function, so the projection on the first coordinate over the unit sphere, complex unit sphere. So and then of course, I mean, in the next step, you try to understand this integral better. I mean, this is also an integral because the gamma function is an integral. But I mean, this gives you a clear idea, and as you will see in a second, I mean, this shows in the Hilbert space case, these numbers are like root of n, asymptotically right, like root of n, like as the Karditz-Nova theorem suggests. Okay, and then the story goes on. I mean, Grünbaum, he proved that if you take ln1, again you get, in the complex case and in the real case, you get different things. I mean, here you integrate these Steinhaus variables on the n-dimensional torus, and here you integrate on -1, 1 these Rademacher functions. Again, you get precise formulas to an integral, and then you can try to evaluate this integral. I mean, here, I mean, this can be rephrased in terms of the zero Bessel function, which is defined here. And here it's just cosine to the power n. And I mean, at the very end here, you even find out that this number is related with the Hilbert space case, because you know these numbers very well, you can calculate this integral. So again, so forget about this, maybe here. Complex case, real case are different. A nice integral, which is not so easy to calculate, but you can rephrase it in something known. And then, okay, now I showed you the case of LNPs for p equal to 1, 2, and infinity. If you go to NP between 1 and infinity, this is also known. Different techniques are needed, which are not trivial. And here you can see that if you take LNP, complex or real, then these numbers are like this Karditz-Nova case, root of n, if p stays less or equal than 2. And then it goes down. For p equal to infinity, it was 1. So if you put here p equal to infinity, you get this 1. There are unknown things. I mean here, this limit, I mean, even the limit is known. If you divide by root of n, the limit is known. The limit is not known if p is bigger than 2. So there are formulas for p equal to 1, 2, and infinity. Real and complex case are different. Asymptotics are known for all LNPs, and here, I mean, even more. Okay, what is the aim of our project? The aim of the project is we want to understand spaces of trigonometric polynomials on topological groups. So trigonometric polynomials, spaces of polynomials, so the projection constant, spaces of polynomials on finite dimensional Banach spaces, and spaces of polynomials which have matrix variables. I mean, this is basically the outcome of our research. So let me show you samples of more specific questions. I mean, if you take a compact group, if you take a topological group and take a subspace of trigonometric polynomials in the space of continuous functions, what is this number? What can we say about this number? So more specific, you take the n-dimensional torus. You take, I mean, on the n-dimensional torus, these z to the power alpha are the characters So you take the span of finitely many characters. What is this projection constant? So very concrete. Another question, I mean, you take the M homogeneous polynomials on some finite dimensional, n-dimensional Banach space Xn, or on a sequence of n-dimensional Banach spaces Xn. So what is this number? How does it behave? Are there precise formulas if you take a precise space? This is much more, of course. I mean, what I showed you is the case m equal to 1. So if you take the one homogeneous polynomials, then you get here, say, the dual of Xn, yeah? And then these numbers were known. Concerning this last point, I mean, if you look at M homogeneous polynomials on all linear operators of Xn, I mean, this would be such a question. So, and there are inspiring examples. The inspiring examples are, if you take the trigonometric polynomials of degree less or equal than m, then, I mean, there's a result of Lushinsky and Kariladze from 1948. This is the number. Another, I mean, in this context, famous result is due to Riel and Wojtaszczyk from 83. If you take the M homogeneous polynomials on the complex ln2, you get this crazy quotient of gamma functions. Okay, and so my personal connection was, I mean, we were working on this Bohr radius, and in the context of this Bohr radius, I mean, it was at some point necessary to understand the projection constant on the M homogeneous polynomials on ln R, if R is between 1 and infinity, and up to a constant, C is absolute constant, C to the power m. This is the number we found. So do these results, what do they have in common? I mean, so for example, this question we were interested in. Okay, now for dry pages come in my talk. I want to show you a general strategy to understand this theorem under one aspect. So the dry thing is that, maybe I should leave this here. The dry thing is that, okay, we take a finite dimensional subspace of some C of k, and we want to understand this number, which is the projection constant of S, as I tried to explain. So, what do you have to, you want to figure out this number. I mean, here's the definition. So you have to control projections onto S. And you try to find a natural candidate such that this infimum is minimized. A natural candidate with fantasy. Okay? And then second, I mean, you need more structure. You try to find a compact group which acts on C of k and keeps S invariant. I mean, by this I mean, in a say, compatible way, you want to assign to every element in the group, that you have to find this group, a linear operator on C of k, such that this linear operator keeps S invariant. So first thing you need some fantasy to find a good candidate for P. Yes?
I'm a little confused. It's always a minimal projection?
No, but I mean, to say, I mean, in this case, yes, this is a finite number. There is a minimal projection. Yes, yes, because S is finite dimensional. Yes. Of course, I mean, you cannot touch it at the beginning. I mean, you don't know. Okay, so you need this idea. You need this idea. Then, I mean, you will understand in a second. You try to show that this P you found is unique. Unique in which sense? Unique in the sense that if it commutes with all these operators, and it's the only projection which commutes with all operators acting on C of k. Second thing, I should have said, I mean, this is inspired by something done in the book of Budin on complex analysis on the unit, on the ball. Okay, so P should be nice concerning this group thing here. And now a great trick comes. And you now take any projection and integrate this composition here with respect to the H-measure. This is a Bochner integral. So you get an operator from C of k to S. And it is a projection, easy to show. It commutes with all these operators. Easy to show. So since we assume that there is only one projection which does this, it is this integral is equal to P. It's equal to P. Okay, last thing, or almost last thing here. I mean, of course, this relative projection constant is less or equal than the norm of P because it's an infimum. But on the other hand, I mean, if P, so P is this integral. So it's this integral. So if you take the norm, you can use the triangle inequality and show you take the norm inside, and then you forget about these isometries, P of G, and you get that this is less than the norm of Q. I mean, you enter with the norm into the integral. And now you take the infimum over all Q's, and the infimum over all Q's, I mean, we started with an arbitrary Q. The infimum over all Q's is the projection constant. So this is the other inequality. So this candidate at the beginning turns out to give you, I do not want to say what you want, because in the last step you should of course understand this norm, because you really want to touch this object, and I mean, to calculate norms is also sometimes complicated. This would be the last step. I mean, analyze P. Okay. Okay. So we call it sometimes the averaging projections technique or whatever strategy. But I mean, in order to unify all these inspiring results, we need more structure on K. More structure on K, which then gives more or less all of this. Let me explain what I mean. We want to refine K, because if we want to assume to have nice assumptions on K, which gives many of these things. What are these assumptions? I mean, the assumption is, for the purpose of this talk, I call K nice. I mean, just here now. If there is a probability measure on K, first thing, yes, and there is a compact group which gives you a homomorphism on K, phi of K, with three properties. So the first, which you can forget in the following, three properties. The first property is that if you take two elements in K, then you always find such a homeomorphism which maps X into Y. First thing. Second, the integral with respect to mu is invariant under putting these homomorphisms. Second thing. And the most complicated thing is, the last thing, find a family of subspaces which are invariant under the composition with phi of G, and the union of them spans C of K. To find nice subspaces which are G invariant in the sense that if you take a function in this subspace and compose it with some phi of G, you stay in this subspace. And the span of the union is dense. So a very nice set of dense subspaces. Okay, if K is nice, okay, maybe it's enough for this talk to say, okay, if you take a nice K, again, let us come back to this averaging technique. I mean, we have a finite dimensional G, now G invariant in this sense, subspace of C of K, with K, a nice K. Find this thing here. In this case, the natural candidate is just, you look at you have L2 of mu. You have this measure on K. And this gives you this Hilbert space. And S, of course, sits in C of K, so it also sits in L2 of mu. So you have the orthogonal projection onto S. And you now restrict this orthogonal projection to C of K. This is a candidate, the candidate which should minimize the relative projection constant of S with respect to C of K. Yeah? Okay. I mean, one needed that G acts on these things here in order to do this trick with the Bochner integral. And of course, here it's, I mean, if you have a nice compact space G, then you can always look at this action. I mean, you assign to every G the mapping which maps to every F this composition. I mean, you have these homeomorphisms on K, and so the composition of F and phi K, this is again something in C of K, and so here you have an action on C of K, and then you have to show that this natural candidate is unique with respect to all projections commuting with phi of J, and then you have this trick that the projection constant, the restriction of this orthogonal projection is this trick, and then of course again you have to find a good formula for this. So this is the strategy, and so one more point, then I'm through the dry part. So I mean, with a little bit, no, I cannot. Oh, I go. So maybe you still remember a little bit these inspiring examples, and I want to show you that you get all these examples with this technique here. But first of all, we stay with this abstract setting. I mean, so the abstract setting is you have a finite dimensional space, G invariant, in C of K, and K is nice. Okay, just nice in this sense. Then, using Rie's representation theorem, there's a reproducing kernel in the sense that, I mean, if you look at this operator, you fix some x here, and look at this operator as an operator on F, as a functional on F, on L2. So fixing x, this is a functional on L2. One can show that it's continuous using the closed graph theorem. This is a continuous mapping on L2. So the Rie's representation theorem shows you that there is something called reproducing kernel. There is a unique element in S such that this formula is true. So this thing here for a fixed x, I mean, this thing here is in fact an integral. And these kernels behave nicely, whatever now nicely means. I mean, they nicely cooperate with the structure we have on K. Yeah. Okay, then one more notion, but this is the last abstract notion. So we call a subspace S accessible if this restriction of the orthogonal projection, so PS is the orthogonal projection on L2 onto S, and here I restrict it to C of K. So if this is the only projection which commutes with the action on C of K, so then you call it accessible. These are the nice things. Okay. And last abstract theorem, I mean, we have a finite dimensional subspace G invariant of C of K. K is nice and S is accessible. Then the projection constant is the restriction of the orthogonal projection constant, and this is the integral with respect to any reproducing kernel you take with respect to X. So it's an abstract theorem which shows you if S is a, say, very good subspace of C of K, very good in the sense that K is itself nice, S is nice, then the minimal projection is the orthogonal projection restricted to C of K, and it's an integral, an abstract integral. I mean, the Rie's representation theorem is behind all of this, so you cannot, first of all, you cannot really touch this kernel, of course. Okay, let me come to concrete things, to more concrete things now. Okay, so this is the main abstract thing, and I claim that our inspiring examples we get this way plus much more. Okay, message is the projection constant comes from this restriction of the orthogonal projection, and it is an integral in such a nice situation. Okay. before I come to really concrete things, this is still a little bit abstract. I mean, you have a compact abelian group. For example, the n-dimensional torus with the Haar measure. We need this phi. We need this phi. I mean, which maps in order that, I mean, we have now a group, so K is G. The group is now G itself. The compact space K is the group itself. So I want to show you a mapping, which is then obvious, from G into the homomorphism on G, which is just multiplication with G. Multiplication with G. And why does it have these three? I needed these three properties to show that K, which is here, is nice. And this is possible. I mean, these subspaces which I needed just come from the fact that all characters in a compact abelian group are dense in C of K. If you have a compact abelian group and look at C of K, then all characters of G are the span of all characters are dense. But here, mathematically, something happens here because this is a deep theorem. This Peter Weil theorem. But these other things, whatever it now is, I mean, I'm sure I'm a little bit too fast, but this is easy. Okay. So again, so now we have a group. K is G, a group, and we have a subspace which is invariant in this sense under the group. Okay, then we proved that then we have this abstract theorem. So this is now just in this situation. We have a compact abelian group, we have a finite dimensional subspace, G invariant. Yeah. So we in this situation know that this S is this K, which you see here, is nice. We know that this S is accessible, yeah, and then it comes to
K is G.
K?
No, it's G. K is
The last line.
Yeah,
The last
K.
K is G, exactly. K is here G in this example. So in a concrete, I make it a little bit more concrete. So you have a compact abelian group like here. You take the span of some finitely many characters, which are pairwise different, say. Then, I mean, if you take this span of trigonometric polynomials, you get this integral here. I mean, you now have to show that this reproducing current is unique. You have to show that it's precisely this, the sum over all these pairwise different characters. Okay, it gets, so this is less abstract than this. Now, another step. I mean, if you take the n-dimensional torus and you look at the span of all monomials, which come from multi-indices alpha, which have such that alpha j is less or equal than dj. Oh, I should put the modulus here. The modulus here, because I mean these are integers. I mean, you are on the torus and have a certain index set. So then an immediate corollary of what we did before is that the projection constant is just the product of these Lebesgue numbers, which are known. And as a consequence, I mean, if you take the case n equal to 1, you get this result of Lozinski and Karel Schwarze in the n-dimensional case. Okay, I will show you many such formulas now, and it's not important that you look at how they look specifically. I mean, here you have the product of all these numbers. I mean, if you put here dj, you get these integrals, and if you evaluate these integrals, you get this product, and blah blah blah. I mean, it's a very concrete thing. And this, of course, is a rectangle, say, a rectangle of multi-indices. The situation changes completely if you, for example, take the unit ball and set to the power n, the Euclidean ball and set to power n, and want to know all multi-indices such that alpha sits in this Euclidean ball. Okay, so we get this result. Now, I mean, we apply this technique to things which we like. So for example, recently many people think about Boolean functions in the context of quantum information theory. And I mean, in the case of Boolean functions on the n-dimensional Boolean cube, what is this? I mean, you have here all n tuples of plus minus 1 with signs plus minus 1. And you take a function of this n-dimensional Boolean cube with values in R, such a function, then it's always it's known that it has a Fourier-Walsh expansion. You can always write it as a linear combination of these Walsh functions. So if A is a subset of the numbers from 1 up to n, you can always multiply the xn. So you take the product n in A and then multiply xn. And I mean, why do I here have this notion of Fourier, by these Fourier coefficients? I mean, this is a compact abelian group. So if you integrate f against this Walsh function, this is the Fourier transform of this character. I mean, these Walsh functions are the characters on this compact abelian group. So to make things easy, I mean, every function on the n-dimensional Boolean group can be written as a linear combination with unique coefficients here of these Walsh functions. And so then you get very nice spaces, finite dimensional Banach spaces here. I mean, you take a subset, you take a subspace F of the numbers from 1 up to n, and look at all linear combinations of these Walsh functions where A only sits in this set, in this subset. So these are all functions on the n-dimensional Boolean cube which only live on the on the subsets of this family. They are supported on this subset of families. Okay, and for people working on Boolean functions, I mean, in particular important are all functions on the n-dimensional Boolean cube with respect to which family. The family is all subsets of cardinality D. So all polynomials on the n-dimensional Boolean cube of degree less or equal than D. All functions on the n-dimensional Boolean cube of which are D homogeneous. Okay. So what is the projection constant here? And again, I have to show you that this K here, to stay in this notation, is nice. And the main point is, one has to find that one has to assign to every element in this group a homomorphism on the group just by multiplication. I mean, this is a special case of this compact abelian group case I handled before. And I have to assure that 1, 2, and 3 that they are satisfied, and they are satisfied. There is no change. I mean, this is a special case of the case where we had a compact abelian group here. Okay. Now, then the abstract theorem shows that the projection constant, if you fix any family here, the projection constant is this integral. The harm measure is just a counting measure on the n-dimensional Boolean cube. So here you see an integral of this thing here. This is the integral of this sum of characters with respect to the harm measure on this group, on the n-dimensional Boolean cube. Okay, then, so if you want to understand this number, you have to evaluate this number here. So this needs a lot of combinatoric, or some combinatoric. But let me give you some idea. I mean, at the beginning, I told you that this limit is root of 2 divided by pi. And what is this? These are the, I mean, if you look at this carefully, these are the one homogeneous polynomials on Ln infinity. On Ln infinity, the one homogeneous. This is the dual of Ln infinity, the one homogeneous polynomials. So you can rephrase it in this way. I mean, these are simply, I mean, this is simply just a moment of reflection. Means the functions on the n-dimensional Boolean cube which are one homogeneous. Yeah. So our question was, what happens if you put a D here? It gets complicated, and here is the answer. This looks nasty, but I mean, what we found is this limit. We are interested in this number, and we found out that this limit divided by basically the root of the dimension of this space, basically, is an integral of a concrete polynomial. I mean, here you see a concrete polynomial which is defined inductively. Don't look at it, but this limit is something concrete. Yeah, and I mean, in the D homogeneous case and in the degree D case, we get the same thing. But if you now put certain D's, so we already saw D equal to 1, which was root of pi divided by 2. If you take D equal to 2, you get a concrete number. If you take D equal to 3, you get a concrete number. We can calculate these numbers. We're solving this integral here. Yeah. So in this sense, we feel that we control these numbers here. Okay, so the strategy seems to work here. Dirichlet polynomials, another thing we're interested in. I mean, so what can you do here? I mean, here I define some space, which you see here. What is it? You fix some frequency. So a sequence which goes to infinity, positive sequence which goes to infinity. And then you fix a finite set of natural numbers, And this space stands for all Dirichlet polynomials which only live on J. I mean, so this is a lambda Dirichlet polynomial, but it's a finite sum, it only lives on J. So it's a finite dimensional Banach space with a nice norm. You just take the soup on the right half plane with a nice norm. So it's a nice Banach space. And the nice thing is that, I mean, if you take, for example, the frequency n, one can do a substitution, this substitution, and you end up with polynomials. So in the case lambda equal to n, you simply look on polynomials in one variable which live on J. And if you take log n, this is the most interesting case, you get ordinary Dirichlet series, polynomials which only live on J. Yeah? Let me make it a little bit more concrete. So once again, this is this. Okay. So find this projection constant. A much more concrete problem is, you stay with log n, so with the ordinary case, the most important case, I believe, in number theory. I mean, yes, you stay, and here I write less or equal than x. So these are all polynomials. This notation stands for all polynomials of length x, of all such Dirichlet polynomials of length x. So where are the polynomials? So how to embed this finite dimensional space in some C of G, some compact abelian group, in order to start this machinery? How to do this? Okay, I try to be fast here. So together with my last PhD student, Ingo Schulman, we defined what we call a lambda Dirichlet group. So a lambda Dirichlet group consists of a mapping from R into G, beta, which with dense multiplicative and with dense range, and a compact group G. And it has the property, if you take such a character on this group, so such a character on this group, it extends to a character on G. So this is a lambda, so a pair beta is called a lambda Dirichlet group. So this is something we invented in order to start an HP theory of general Dirichlet series. So once again, I mean, it's a multiplicative mapping, dense range. Every character of this thing, this type on this group here, extends to a character, unique character then, because I mean the range is dense. So we call it H of lambda n. And then, so the good news is every frequency, for every frequency there is such an object, such a beta and such a G. There is always one. It's called the Bohr compactification. There is always one. If you take a concrete beta, for example n, you find much nicer groups and betas than this Bohr compactification. If you take for lambda log n, so the ordinary case, then there's something called the Kronecker flow. I don't explain it. So then the infinite dimensional torus is the perfect group here. Good, perfect in the sense that the analysis you get is very nice. Although, I mean, the Bohr compactification is a lambda group for every lambda. Okay? So then you can use this group to embed h infinity j into C of g. You just take such a polynomial, which only lives on g, and assign to every object here this h of lambda n, and the h of lambda n lives on g. So you get the polynomial on g, which is isometric, simply because of density. And then everything starts. And so we get that if you take any subset and any frequency, that the projection constant is this limit here. I mean, yeah. And this has to be proved, I mean, of course. I'm basically an integral, take this limit as an integral, is an average of integrals, an integral of the sum of certain characters. The philosophy is always the same. Okay, but it gets now, so our best thing here is that if you apply this to log n, so the h infinity, so this space stands for all ordinary Dirichlet polynomials of length less or equal than x. Then this integral, this is this theorem before. I mean, now these things here are this thing, and it's this number. This integral is this number, and there we connect with a very recent deep result in number theory. So Harper, he in 2019 calculated, in fact, this integral. So our abstract setting leads us to this integral, and here this we get for free. This is asymptotic, and this solved this solves several problems in number theory. I mean, one problem was Helson, he conjectured that this integral is root of x, and it's not true. It's this number here. Yes, but the thing is connected with the embedding theorem, with embedding conjecture, and so this is really a breakthrough, which here helps. I mean, this projection constant of the Banach space of all ordinary Dirichlet series of length less or equal than x is this number. Okay, I check my times. Okay, we do something else. I come back to, I want to show you that this Ril-Wojtaszczyk theorem is can also be proved or improved here, proved and improved here. So we want to find the projection constant of all polynomials of degree less or equal than d. I say our polynomials now, yeah, because there are many polynomials around, or all d-homogeneous polynomials on level 2. I mean, so what can be? This is a function in the dimension and in the degree, so it's complicated. Yeah. Okay, so what in the complex case? Again, I mean, the general framework is, I mean, now the K is the n-dimensional sphere. The K is K, and the group is the group of unitaries. And I mean, every unitary operator, say on LN2, the group of unitaries. And the unitaries, I mean, the mapping is, if you start with a unitary, you just take the mapping which assigns to every set U of Z. So U of Z is also in the n-dimensional sphere because the unitaries are isometries. So this is a well-defined mapping here. Yeah. And this is the mapping we are looking for. I mean, again, this 1 and 2 are satisfied, here it gets very interesting. I mean, in the book of Rudin, you find that, I mean, I need subspaces which have a span which is dense. Or if I take the U, in other words, if I need subspaces, here they are called HPQ. If you unify all of them, then the span is dense. And what are these subspaces in this case? The subspaces is, you take all harmonic functions on Cn, which can be represented in this way here. Okay, a beta is missing here. So it's a sum of coefficients Z alpha, Z bar, beta, taken over all alpha and beta, multi-indices of order. So the sum, this is the sum of the alpha j's, is equal to P, and here equal to Q. So you take all functions which are harmonic and have a representation this way. So this is a space of functions which, and so you take all these functions and restrict them to the sphere. So this space consists of all functions on the sphere which come from restrictions of harmonic functions with this representation. And if you take the union of all of them, then the span is dense. This is in the book of Rudin. Okay, so what is the projection constant of this inner subspace of the space of continuous functions on the sphere? And now I come with what we got. I mean, so if you take all polynomials in the complex case, all polynomials of degrees less or equal than d, then it's this crazy integral. I mean, you have numbers which depend on n, you have a sum, the numbers which depend on n, and then you evaluate this function. This is the projection to the first coordinate on this thing here. Okay, we can improve this result. These are polynomials of the degree less or equal than d. We can improve it, and at the very end we get this. I mean, this is a special case. This real Wojtaszczyk case is a special case of. I do not explain this now. Of this result here. So, but we get this just starting our process in the right way. Okay. So I hope one can understand the philosophy. So we have an abstract approach which leads to all these things and improve them even. And the real case is different. I mean, if you want to understand the real case, then we have to take the orthogonal group, not the unitary group, the orthogonal group. So we take an orthogonal matrix and which assign to it the homomorphism which maps to x. Say O of x here. And here, again, this number 3 is the most important thing. I mean, this is deeply connected with the approximation theory now. I mean, in this case, the subspaces we need are defined as follows. They are restrictions to the sphere, they are functions on the sphere, restrictions to the sphere of K-homogeneous polynomials, K-homogeneous in our sense, as always, as we use it, I mean in this group here, but they are harmonic. So you take K-homogeneous polynomials on Rn, which are harmonic, and restrict them to the sphere. So approximation theory gives you, if you take the span of all, the union of all of them, and then the span, they are dense. And again, so what is this projection constant here? And it doesn't matter what it is. I mean, there is one outstanding polynomial in this business. This is the Legendre polynomial in n variables, defined here. Forget about it. I mean, it depends on the dimension n and the degree d. Here is the definition. It's one of these polynomials, which are defined here. And you can rephrase this in polar coordinates. In polar coordinates. I mean, this is this thing, and this is simple. In polar coordinates. And another thing is that this subspace has a certain dimension. This is done in approximation theory. Here is the formula for the dimension. And if you go to the projection constant now, then you again get this dimension and this Legendre polynomial sum integral. You can rephrase this space of polynomials of degree d on this sphere as an integral. Yeah. And since d-homogeneous polynomials always take their sup on the sphere, you get for the d-homogeneous polynomials, if you look at the d-homogeneous polynomials on Ln2 real, and look at the projection constant, you get nice formulas. And I mean, if you evaluate this formula which we got and go back to the case d equal to 1, if you take d equal to 1, you have the dual of Ln2 here, Ln2 real. If you are again in this case, you get this formula here. Yeah. Okay, so I take 3 more minutes. So then again a very different thing. I mean, if you look at the trace class, the trace class are operators on Ln2. Trace class. No, Schatten P class. Okay, Schatten P class. We are operators on Ln2, and this is the norm. This is, in a sense, the little LP in non-commutative functional analysis. The little LNP non-commutative functional analysis. So the P Schatten class are all operators on Ln2, such that if you look at the eigenvalues of this operator here, the SKU, and take the P norm, this is the norm. So if P is equal to 1, these are the nuclear operators. The nuclear operators. If P is equal to infinity, these are all operators. If P is equal to 2, Hilbert-Schmidt operators. And there was one problem here. I mean, they know, I mean, since many, they know the projection constant of this Schatten class. It's n for all P. Asymptotically, it's n. They know this. I mean, in the case of S infinity, this is an epsilon, these are all operators on Ln2, this is an epsilon tensor product, and projection constants are stable under epsilon tensor product, so you just have to multiply what you get for the Hilbert space in order to get this known. Hilbert-Schmidt operators is a Hilbert space of dimension n squared. You can take the old formula. And for the trace class, they knew this. They knew that, I mean, it's n, but it sits between n and n over 3. And we get, with our strategy, that if you take the trace class, the nuclear operators on Ln2, then the projection constant is this integral here. You take the trace and integrate over the unitary group and multiply with n. And then we got this limit here. So with probability theory, if you, I mean, I told you that, I mean, here you know, the limit is known for infinity, for 2, it was not known for p equal to 1. But with this formula you get it. And this fits perfectly into the picture, into the whole picture. And so last comment, I mean, let me just show strategy again. I mean, we embed the trace class into the continuous functions on the unitary group. I mean, for those who know this, I mean, the nuclear operators on Ln2 are the dual of the operators on Ln2. So if you restrict these functionals or operators on Ln2 to the unitary group, you get this embedding. I mean, these are functionals. This is the dual of Ln2. And if you restrict these functional to the unitary, you will get this embedding here. And then we need an action. This is a non-commutative case. We need an action of a group. So we define this action here. This is non-commutative. Now, we define this action, and then again we have to go through 1, 2, and 3, and define them, and it works. I mean, at the very end, we get this formula. So this is enough. Thank you very much.
Thank you very much. Question, comment, remarks?
But just sorry for my question before, because I overlooked that S was finite.
Yeah, no problem.
I have a question is, a bit unrelated to your talk, but related to this projection constant. Because many years ago, I think it was 30 years ago, with Paweł Domański, we faced the following problem. We know that for x equal c naught, so this is of course not the case that you are always working with finite dimensional, for x equals c naught, and if you consider only subspaces which are separable, I think there is a universal constant which is 2. The universal position constant for c naught, considering only y's the separable.
Okay, I don't know.
But for, if you consider all Banach spaces in which c naught is complemented,
it should be infinity.
I don't know. I mean,
I mean, if CZ, so if CZ, if you, I mean, in bed C0 in L infinity, it's not complemented.
Yeah, but the thing is that if you consider only those subspaces in which C naught is complemented.
Okay.
Okay.
And then,
the family of all Banach spaces in which C naught is complemented.
Yes.
Then.
Yes.
I mean, if it was related to something about the prototype problem of topology, projections and examples and things like that. So, but we were asking people who are expert in these things. And
of course, there are many things here. I mean, this projection constant is one of the crucial notions. I mean, maybe at the beginning I should have said that I mean, it started. So Banach asked, I mean, does every Banach space have a complemented subspace? And Hilbert spaces are the only Banach spaces such that every subspace is complemented. So if something is not a Hilbert space, something
this is Lindenstrauss.
Yes, Lindenstrauss. So Pyczynski Lindenstrauss.
Lindenstrauss for sure.
Yes. So, but and now, I mean, there are many things of course known, and I do not know many of these.
Yes. In case that you were facing this in your way.
No, in fact, I personally was happy that I could touch the projection constant, but because I was always interested in it, I never, I mean, stopped dealing with it. So. It's. I mean, maybe I should say this. I mean, in the book the four of us wrote, I mean, there is a connection. Because I mean, you have this Bohr radius. The Bohr radius is connected with the unconditional basis constant of polynomials, and what we then did in this book, we estimate the unconditional basis constant of the m homogeneous polynomials by the projection constant of the n-1 homogeneous polynomials, and this is a way to understand that the Bohr radius has this log term. But I always stop there. I mean. We then used the Kabitz-Nova, and then this is something I originally did with Leonhard Frerich. And so this is, so for me it was interesting.
¿Alguna pregunta? Algunas gracias, Andrea. Thank you very much.